Okay, now we are in the uh, learning on the reference state and also the implications, okay, for the reference state. Now, one applications of the reference state is by looking at the tables, okay, the steam tables or the saturated steam, superheated steam in table B5 and B7. If you are um, having your textbook now, you can check the textbook. Oh, by the way, is my screen clear, or is my voice also clear, or is there any delay? Okay, okay, okay. Thank you. Okay, so perhaps before we move on, let me just give you some context on what does it mean on the tables. Okay? So basically, we have the equilibrium, okay, for vapor liquid. So we have the vapor liquid equilibrium. So we have uh, the left part is solid, subcooled liquid, and this is called the saturated superheated steam. And in this equilibrium, at right moment before it crossing the boundary, we call this the saturated liquid. And if we crossing uh, the line, it's called the saturated steam or vapor. So actually, we might have in this line here, we might have some percentage. Okay, how many is still liquid and how many still steam? So that is actually uh, will be that will be in our observation as well. Okay, but perhaps the implication of this equilibrium is directly related to the table B5 and B7, B5 to B7. Okay, and you will see the relations between the pressure and the temperature, as we can see here, pressure and temperature. So whenever you have um, examples like a problem set that is not really mentioned, uh, like the given information is not sufficient, then you must try to look at some reference, okay, because we already take notes on reference state. So probably we can take notes also for some um, some table specifically for the steam, okay, or for any steam or liquid if we have, then we will look at B5, B6 for saturated steams and B7 for superheated steam, and we can find the specific volume, the uh, internal energy, the enthalpy. Okay. And after we use that information, we can put information into our solutions. Okay. 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 Let me start today's lecture by uh, taking on the procedures, so energy balance procedures. Okay, if we have this um, problem set, we have two streams of water are mixed, okay, to form the feed to a boiler. Uh, we have some data sets, stream 1, stream 2, boiler pressure. The exiting steam emerged from the boiler through, we have this diameter, the internal diameter, and then calculate the required heat to the boiler in kilojoules per minute. So this is the unit that we are going to follow if the emerging steam is saturated. It's a key point, to understand our problems. And the boiler pressure, neglect the kinetic energy, so we are going to ignore the kinetics. Okay. So I think from here we can take into some diagram. We may state what is the core is the boiler, right? Because this is the one that we are going to feed, and then the one that we are going to emerge. The process is going to boiler and out from the boiler, right? Out of boiler. So we may take this into a schematic diagram. And then we have two streams, right? Stream 1 and stream 2. So stream 1, we have 120 kilogram per minute, 30 degrees Celsius. And we can check for this temperature, we can check the enthalpy is 125.7 kilojoule per kilogram. And the second stream, and this is at 65 degrees Celsius. And you can also mention that it's still liquid. This is still liquid. So liquid, and then enthalpy for the second stream is 271.9 kilojoule per kilogram. And then going outside, emerge as steam for I think that's the first case that we are going to find. So first is the pressure, 17 bar. Because it's saturated. This is on 204 degrees Celsius. You can check the table. It's on 6 centimeter diameter, internal diameter pipe. And determine the flow rate. Determine the flow rate. So first determine the flow rate using material balance. And I think because it's just 120 and 175, we can set up this to be 295 kilogram. And this should be vapor per minute. So I think we have I forgot to write the enthalpy again from the table. We got 2793 kilojoule over kilogram. Okay, I think it's done for the first steps. So the first step is actually finding the flow rate. Let me write here. The first step is determine flow rates of all components. So we have this, and this. That's the flow rate. Second, determine specific enthalpies. And because this is saturated, it's saturated here, then we are determining this enthalpy from table B5, and B6. That's for saturated, right? So determine at 30 degrees Celsius, 65 degrees Celsius, and saturated steam at 17 bar. And this correlates to 204 degrees of Celsius. And then the next steps is, so after we draw the schematics, write all the necessary, the flow rates, the specific enthalpy. So after we got all the requirements, then we can write the general formula for the energy balance. Okay, so formulate the energy balance. Right, maybe here. So the heat minus, or its flow, like that, because all is with certain of time, right? So the heat flow, work shaft, and then the kinetics, or maybe H enthalpy, kinetics, and then potential. And we may assume, if there's nothing given in the information, so we can assume that the work shaft is 0, the kinetics or the potentials is 0, and then we can write down the formulations to be the heat flow is equal to this change of in enthalpy plus the kinetics, because we only neglect the kinetics on liquid inlet streams, right? Okay. So we may focus on the outlet. Okay. Now first, to see or to observe, we start looking at the enthalpy. The enthalpy is using this approach. Okay. This is outlet, and this is inlet. So every time we are solving our energy balance for the change in enthalpy, it is always the outlet minus the inlet. Okay, so we need to focus on finding which one is the outlet, which one is the inlet. So first, the outlet, the flow rate is 295, right? 295. And the specific enthalpy, this should be specific like that. Sorry. Specific enthalpy is 2793 kilojoule per kilogram. Okay, I think this is for the outlet minus the inlet. Let me write a little bit left. Okay, and inlet, we can write this is 120 kilogram per minute, and then write all, sorry, it should be kilojoule, and plus okay. Now we can calculate. If you have calculators, you can calculate this, and it's supposed to be 761, or if you want to make it this decimal, 7.61 and kilojoule per minute. Okay, first we have, and then for the kinetics, we focus on the outlet stream. So on outlet stream, we have the pressure is 17 bar, and from table B6, we will get the specific volume that is on 17 bar is 0.1166 meters cube per kilogram. The radius of the pipe is 3 centimeters, right? The diameter is 6. So this cross sections area is pi r squared. It's supposed to be 3.14 something. Multiply with 3 squared, and use some conversion to denotes that this is 2.83383. Okay. Now, because we have the cross sections, then steam velocity is the volumetric flow rate divided by A. Okay. Now this is also important. So whenever you find that all of your terms is defined or described as flow rate, then all the things that you need to account is actually you need to use the flow rate. Okay, so the same structures. So this will be equal to 295, the flow rate per minute, 1 minute 60 seconds. This is the mass flow rate, right? And this is the specific volume. Specific volume is 0.1166. So I think we can have all here, right? Okay. And then divide by the area. The area is 2.83, and we can have meter per second. So we can compute all of it. Then this will be equal to around 202 meter per second. And this is just a velocity. Let me put here velocity. Now from the velocity, we can reward our change in the kinetics, and as supposed to the information we have, then this will be equal to the kinetics on the outlet, right? Only at the outlet streams, which is the mass flow rate and then the velocity squared divided by 2. So we are calculating 295. If you want to write divided by 2 kilogram per minute, and then 202 squared meter squared second squared, and exchange all using kilojoule. So we need to use some conversions. So Newton, kilogram per second squared, kilojoule, 1000 Newton meter. So kilogram and this is M, and yeah, I think already all. So this will be equal to 6.02. Now from here, we get the kinetics. We also get the heat flow, and that is our total solutions. So we can write here probably that the heat, the Q here, the heat flow is equal to the enthalpy, change of enthalpy, plus the change of kinetics. I think both already in kilojoule per minute, so you can write. So actually, if you look at the numbers, okay, and this is sometimes you can also use some logics when you are solving these equations. So you have these formulations, right? You have heat, work shaft, enthalpy, kinetics, potential. Now what we have here is the enthalpy and the kinetics. Say the numbers. This is 10 with power of 5. This is 10 with power of 3. This is much more higher. It's at least 100 times higher, right? And that is most of the case is happening. So actually your enthalpy will be more significant rather than the kinetics or even potential. Potential is very small actually. Kinetics may be a little bit heavy, but not as heavy as enthalpy. So if we take this, it's not much significant. It's still in the digit of 7.6 something. It's just changing several decimals, right? See here. So you can actually confirm whether when you calculate if there's any mistake or is there any weird situations you have. You can actually realize that if you have the enthalpy, it should have much more significant numbers than the kinetics. Okay, it's basically in engineering that logic seems can confirm for what we have. Okay. Okay, any questions from here? So the key, first, draw your diagrams. Second, determine all at least the flow rates for each component. Second, the enthalpy, that will be very significant clue. Enthalpy, it can be described in the table. If you have given information, then you can find in the table. And then the third one, formulate the energy balance. And to formulate, we always start from this equations. Okay. Okay, now we move on to another sections, which we call the mechanical energy balance. Okay, the mechanical energy balance is basically some small part in our energy balance that is related to some small components, usually small components, some mechanical components. So like I said before, usually if we have some flows like delta H, okay, we have the change in the enthalpy, and we have another kinetics, and or maybe we have the shaft work, right? We have the kinetics, we have the potentials. It seems that this enthalpy is much more significant, right? Like also from the previous procedure example I showed you before. So we can sometimes usually write the heat, the total heat is just the difference in the internal energy for closed system, or is equal enthalpy if we, sorry, for closed system not did not having any flow, sorry. So this is open system. We sometimes just write this to signify that, okay, the heat is actually change of internal energy, or the heat is the change of enthalpy. Okay. And now, if you would like to observe on how this can probably have some importance if we are having some process, and probably from the whole process, if you would like to restrict and just observe the small things here, just to observe this part, we can have some balancing for those energy balance. And this is how we can apply with this mechanical energy balance. Let me write the whole. This is equal to right. Okay, consider we let M be a mass flow rate, and V as specific volume, and V, we can imagine V can also be represented by 1 over density, right? 1 over density is it have some similar structure. So this is liquid density. Now the equations can be written as, and this is also you can try by yourself. Okay, I hope you can try to manipulate the whole things here. Probably first divide all by m, and change the volume to 1 over rho. You will get the structure of the pressure divided by the density plus the kinetics plus, this is actually from the left one, and some sort of changing the some terms, okay, and this equal to, this is delta U specific internal energy, and then minus Q over M, and this will be equal to The shaft work is work done by fluid on moving elements in the process line. And sometimes the terms these terms here, it signifies, okay, it signifies or maybe let me write in terms of a better approach. So imagine that we have the potential and kinetics. So this is actually related to kinetics. This is potential, right? Okay. Now, usually, kinetics and potential, if you remember, let me explain. Maybe explain with the simple physics. If we have a box, okay, we have some force over there, and sometimes if we have some frictions, and if we correlate this through some energy conversions, perhaps with work, right? Perhaps we can also look upon that these frictions can be felt as the heat that we release, right? We have some increased temperature, right? Okay, I think quite logic, right? Now this is actually the same or similar phenomenon when we have the kinetics, we have the potentials, okay, and they both usually converted to thermal energy, converted to thermal energy. Okay, as a result of a friction. The friction of the fluid, okay, because if you imagine this is a pipe, we have a fluid here, right? Then the frictions between the fluid and the pipe, that will be increasing in thermal when the fluid is moving, okay? Now, in consequence of that thermal energy, we need to have these terms, okay? So because of that frictions, well, let me say that this has frictions here, the friction. Now to balance these frictions, we need to have another thermal energy that is simply put on these equations. This is to, let me write with green. This is to balance the friction. The friction between fluid and stream, not stream, pipe, or maybe streamline, maybe streamline or pipe. Okay, maybe that's more clear to be imagined. So sometimes this term, the whole thing here with the blue box, we can write as just one symbol. With F. And we call this F as the friction loss. And thus, we call this as a general terms for, or general formula for mechanical energy balance. and it should be valid for steady state flow. Of incompressible compressible fluid. And sometimes to simplify, we can usually ignore the friction loss and the work shaft. So sometimes we can have another form that ignore this friction loss and take the work shaft as 0. So we can write the whole equations and that's depend on the case. Okay. This is we call the this one. It's called the Bernoulli equations. So whenever you find a questions that stated the friction losses negligible or you can ignore that, means you are going to use this Bernoulli equations. Okay. So mechanical energy balance. Of course, if we compare with uh, the classic enthalpy in the whole system that stated whether it's open or a closed system. Mechanically, if you look on each component, it's relatively small. Okay? The heat is relatively small. But sometimes in a process, if you are observing some industrial process, you need to know what happened in each side. And of course, if we want to observe locally, then we need to check using this mechanical energy balance. Okay? It will be different. It will be different if we are going to compare with the whole process, okay, in the whole system in which we can describe the process using the enthalpy or internal energy if it is the closed system. Okay, maybe giving you one example on this mechanical energy balance. Okay. Perhaps this the last section on today's class. And maybe the example from the textbook maybe I will give to you next week. And be prepared for a quiz. Maybe next week or next 2 weeks. I will put information later. okay, in the middle. But let's start with the equations from here. So estimate the pressure required at point 1. Actually, point 1 is here. So it's asking pressure 1. So we have height, difference in height. We have pressure 2, all the cross-section area, right? So perhaps before we are going for the balance equations, perhaps we can calculate the area, the cross-section area. So we can check the area and velocity, maybe just velocity to be clear, velocities. So first is velocity 1. We have 20 liter per minute. 20 liter per minute. So we are going to exchange liter to meter cube, and this should be divided by the cross section is pi, and this radius is 0.25 squared. It's centimeters squared. We need to also change to the okay, maybe here better to write. Okay, and then this, oh sorry, convert a minute to a second. Check all the conversion whether it's correct. Okay, I think it's correct. We can calculate. This will be, turns out to be 17 meters per second. The second velocity, still we have the same amount liter per minute. Convert. The difference is in the diameter. This is 0.5 radius. This will turn out to be 4.24. We can have the difference for the delta V squared, so we can have 4 minus 17 squared. So this is 2 minus 1. 2 minus 1. This will become negative 271 meters squared second squared. Now we are going to involve the energy balance, which we can write. First we can write delta U squared divided by 2 plus G delta Z. Okay. Now we can write down that delta P is P2 minus P1. And rho, the water is 1000, density of water. Delta SV. Actually, your textbook using U, but I'm not used to write U, so let me just write V velocity, small v for velocity. Take the gravity as 9.81. and the delta z, z2 minus z1, I just take 50 meter. So we are going to put the P2 minus P1 divided by 1000 kilogram per meter cube minus 271 divided by 2 becomes 135.5. That's the, and the gravity and Z is around 490. Should be equal to 0 because we can neglect the friction loss. Okay. So P2 is 1 atmosphere. We can write 1 atmosphere, convert into Newton. And P1 is, from the equation here, we can solve that P1 is 456, or it's equal to Pascal, or this is equal for around 4.5 bar. Okay, that is the example on the mechanical energy balance using the this is precisely the Bernoulli equations. The Bernoulli equation. Okay, any questions? If not, then perhaps this will be the last part on chapter 7. So as in schedule, next week we still have some example and practice, okay, for Monday class for chapter 7, and maybe just a little bit intro to chapter 8. And Thursday, I think we can just still focus on chapter 8 for Thursday. And Monday, 2 weeks later, we'll have a quiz on chapter 7, okay? Because this week you have the midterm. So the quiz will be next 2 weeks. So every time we finish chapters, we will have at least 1 or 2 weeks after that one quiz. Okay? So we will probably will have chapter 7, chapter 8. At least that is the quiz, a quiz chapter 7 and a quiz chapter 8. The last part, chapter 9, will be, I think, I will just directly go to the final exam. Okay, but if we still have time, we can have another quiz, okay, and see whether your score need to have more exam. Okay, if not, then I think just having 2 quiz with me and then final exam. Okay. Okay. So is there any questions? Any questions so far? If no, then oh, sorry. I just read your question. Rivaldo, sorry. Yeah, V5 and V6 is only for the saturated and steam. It's all for water. Okay, if there is no questions, let me show you again the QR code. Okay, and hopefully you can have good grade for your midterm. Okay, good luck for the midterm. And my suggestions before our quiz, So our quiz, chapter 7, you already prepare the table, okay? The table you need. But I'm just suggesting just copy all the table on the appendix. So from I think from B1 to B11, I think B1 to B11, you can copy that. And every time we have a quiz or exam, you need to bring all those tables. Okay. Okay. If there's no questions, then you can leave the meeting. Okay, and thank you for joining the class. Okay, thank you for joining the class today. Yeah, sure. You're welcome, Michelle.